I think I'll pass. It's awesome, though. I'm impressed. I think it's good. I wish I could. Years ago, when our kids were young, the most dangerous thing I did was do they still do the blades, like the roller blades?
Oh, yeah.
Yeah.
Actually,
it seemed pretty dangerous.
I did that one time when I was little, back when we were in Las Vegas, and I was just like, we had this like little driveway that was kind of at a slope, and we had a wooden gate, right? I don't know how this happened, but like I was on the rollerblades, and so I was just going down the little driveway thing and put my hands out to stop myself, and then I got tons of slivers, like tons, like my hands were covered in slivers, and like my mom was like spending hours just like picking them all out. And
how old were you? That's terrible.
Yeah, I don't know. I was young. I was younger than like 6 at least. Because we moved when I was like almost 8.
That would make me not want to do that anymore.
Yeah, I didn't.
The last time I did that, I was at my friend's house and we were going down like a hill and I was starting to fall and I accidentally pushed her all the way down. And so then I stopped after that. I was like, she fell and I didn't.
Well, what are friends for?
You're gonna do what you're gonna do.
Human. Oh my goodness. Oh, okay. So let's pick up where we left off. Yeah, this is part 7. So I'm looking actually at the online homework, and there's 2 part 7s, and I'm going to get mostly through I'm going to stop at problem number 3 today, but I went ahead and assigned several parts. So if you want to do these, then if you do an online, they would be due Friday. Wait, Wednesday. Yeah. Does that make sense? So just let me know if you have any questions. I'm a little flexible. But anyway, so there are a lot of buffer solutions are important in life. The other day when you did your red cabbage experiment, the pHs that were under the first hood, those are all buffered solutions, which just meant that they buffered solutions like this says will resist pH change. You can drip in H+, you can drip in OH-, and it resists pH change. Like, how does it do that? Okay, so if I'm a visual person, and so maybe some of you guys are too, so here's my beaker, and then here's a buffer, and just like the slide says, I'm going to add H+, and this is going to stay, pH is constant. You're like, how could that be? I add OH- and pH is constant, okay? I don't know a lot about biology, but I'm pretty sure like our gastric juices in our stomach, it's buffered. So if we eat something acidic, it stays acidic. If we eat something basic, it stays acidic, okay? And speaking of red cabbage, so this yellow here actually is just methyl orange, okay? And it's at a pH of 8. So the methyl orange is just going to show us how acidic or basic it is. So this is unbuffered and this is buffered. So what we're going to do to both of them is we're going to add 1 milliliter, which isn't much, of 0.01 molar strong acid, HCl. So here we go. So again, the buffered solution, we added this HCl, it stayed the same pH, as indicated by the same color. The unbuffered, we added, it became acidic. There wasn't anything, and this isn't magic. Buffered solutions aren't magic. Go ahead and tell you, all buffered solutions is they basically have, not receptors, but they have the ability to neutralize acids and to neutralize bases. That's it. That's how they're made. So what is a buffered solution? Well, what a buffered solution needs to be able to do is to handle acids. Okay, sorry. It must contain an acid to handle bases. So let's see a different color here. So in here, we need to have some sort of acid to react with our base. We need to have some sort of base to react with our acid. And those guys need to be able to coexist. That's it. Okay, so you need to have something down here that can intercept or neutralize your acids or bases, and they need to be able to coexist. So what works well, we've been talking about a pair of species that differ by a proton called the conjugate acid-base pair. That's great. That's exactly what works great. Because your conjugate acid will be good to work with neutralized bases. Your conjugate base will be good to absorb that sort of activity. Okay, so conjugate acid-base pairs. So if we pick on acetic acid, so acetic acid is CH3COOH. Its conjugate base is minus a proton, CH3COO minus. Okay, so the acetate ion. According to, here's the chemical equilibrium we have between acetic acid and its conjugate base, all right? According to Le Chatelier's principle, if we add the hydrogen ion or the hydroxide ion, it's going to stress the system. So let's see what that looks like. Let's go ahead and add the hydrogen ion, okay? Hydronium cation, hydrogen ion, it's the same thing. So what's going to happen then is it's going to shift more to this side, okay? So if we add more of this, it's going to go, if we add more product, it's going to go to the reactant side. So what's going to happen is you're going to get a new equilibrium established, and notice now your acetic acid is a little bit higher than your acetate, but it's still there. And we're going to talk about buffering capacity. So as long as you have not like doused it with the hydronium ion, hydrogen ion, same thing, beyond its buffering capacity, it's just going to kind of hover that way. So let's go ahead and look at the other thing. So if we add hydroxide to it, what that's going to actually do is force the hydrolysis of our weak acid, okay? And so we're going to have more of our acetate ion form. So here we go. There's your acetate ion. Up more, your acetic acid down less. So this kind of going back and forth for your conjugate acid-base pair, the molar concentration, that's what's happening in your buffered solution as you drip in acid or base. So I double checked with Carl last night. I'm like, we don't give him this, do we? And the answer is no. So, and then it's not really funny. You're going to want to memorize this relationship. It's called the Henderson-Hasselbalch equation, and it has to do with buffered solutions. And it's a big one. I'll go ahead and write it on the board. So I call it the HH equation because Henderson-Hasselbalch is a mouthful. And like I said, it's for buffered solutions. Specifically, the pH of a buffered solution will be equal to the pKa, so the P function applied to the weak acid, plus log base 10 of the ratio, and I'm just going to put base, the ratio of the molar concentration of the base divided by the molar concentration of the acid. Okay, that's the Henderson-Hasselbalch equation. All right. So again, it applies to buffered solutions. Let's see what that, let's look a little bit more at what the Henderson-Hasselbalch equation is all about. And I didn't do it for you guys this semester, but if I would, I don't think I'm going to do it. But so if I would take the equilibrium constant expression for a weak acid, remember weak acid is, well, I'm not going to do it, it just drives me nuts. You guys don't want to see me derive that. But if we take the equilibrium constant expression for weak acid and rearrange it, we get the Henderson-Hasselbalch equation. Maybe I'll do it and bring it and show you on Wednesday. So here's the Henderson-Hasselbalch equation. Now I'm going to show you another form of the Henderson-Hasselbalch equation. So the molar concentration of the base is the number of moles of base divided by the volume. The molar concentration of the acid, number of moles of acid divided by the volume. Assuming these are the same volumes, check this out. Our Henderson-Hasselbalch equation takes on sort of a different form. So what you're going to see on the next slide is, and I'll write it over here on the board, is basically the Henderson-Hasselbalch equation, but here the log base 10 is going to be the ratio of the moles of base to the moles of acid. It's just another form. of the Henderson-Hasselbalch equation. So either one, and whichever one you use, it just depends on what information you're given. I think probably if I'm memorizing something, which I do not like to memorize things, one of the easy or the hardest things to do is to try to remember what the ratio is, and it's base over acid. Okay? So either one of those are great. So in order for our buffered solution to work and our Henderson-Hasselbalch equation, these are only 4 buffered solutions. Sometimes students get confused on when do I use the Henderson-Hasselbalch equation. It's only for buffered solutions. How do I know I have a buffered solution? You have a conjugate acid-base pair, basically. So one of the things we've been talking about already is the weak acid, how it ionizes to form its conjugate base and kick off a proton. That amount of ionization of the acid needs to be relatively small. We've been kind of talking about how X is relatively small. Similarly, when the amount of conjugate base or base that will undergo hydrolysis needs to be relatively small too. If those are relatively small, then actually we would expect them to be relatively small. The ionization of the weak acid or the hydrolysis of the weak base because of the common ion effect. And that kind of goes to, I'm going to show you that we need to have kind of similar amounts in here. So when I put OH minus, actually that is the weak base. And when I put H plus there, actually that's your weak acid. And this is a conjugate acid-base pair. One of the things, and this goes back to the common ion effect, is they need to be present in our buffered solution in similar molar quantities. All right. So it's kind of a weird cat, and this is one of those things in chemistry. It's going to be easier to show you than it is to kind of show it to you in action, the Henderson-Hasselbalch equation in action. So can you see where the pH of this buffered solution, okay, depends on a few things. One depends on the pKa of the weak acid. Well, that's not going to change. But the other thing, like this slide says, is it depends upon the ratio of the conjugate base to the conjugate acid. So the pH is driven by this. Okay. The buffering capacity, and it's the word capacity kind of implies how much can it absorb when you're dripping in H plus or OH minus, actually depends both on the ratio of your base to acid and on the molar concentrations. So capacity is how much you can go ahead and add the hydrogen or the hydroxide ion and it remains the same pH. And if you want to optimize your buffered solution, here's how to do it. You want this ratio, the ratio of the molar concentration of the conjugate acid and base that's in your solution, you want it to be as close to 1 as possible. So I'm going to say, my target is to shoot for the number 1. I already mentioned that you want them to be in similar molar concentrations. And here's the cool thing about it. The log base 10 of 1 is, do we know? Log of 1 base 10 is 0. Yep. So as this approaches 1, then this term approaches 0. Now, will this be 1? Probably not, but the closer it is, the better buffering capacity you have. The larger the concentrations then of these things, keeping the ratio 1, then the better the capacity. This says actually that if you get this ratio on either side by a factor of 10 off, then you don't have a very good buffered solution. So this is to say that if this ratio is 0.1, or if it's, I guess I should say this, if it's less than 0.1, that's bad, okay? And if it's greater than 10, that's also bad. So that's kind of what I mean there. All right, so this is another kind of thing I showed you earlier. We've got the color going on for us to indicate what the pH is. We've also got the pH probe sitting in there telling us what the pH is. So here we have pH of 8, pH of 7.6, pH of 1.53. Notice that what we're doing actually is adding just a small amount of acid. We're dripping in acids in each of these cases. But what's happened to the last one is we have gone beyond the capacity of that buffered solution to go ahead and neutralize. So there is a limit. It's not like limitless. So these are the two forms of the Henderson-Hasselbalch equation that come in handy. But they're both saying the same thing. But again, if these only work, this relationship only works for a buffered solution. So if you're asked to create a buffered solution, and I said down here pH is constant, but whatever your target, how do I say this? There it is up here. Whatever your target pH is, okay, your target pH should actually be equal to the pKa of your acid. Do you guys have this one? Okay, good. So the reason for that is I told you that as this ratio approaches 1, then the log of 1 is 0, so that term falls away, so then your pH is equal to your pKa. So whatever your target pH is, you find an acid, conjugate acid, that the pKa is equal to your target pH. This little hint says, with regard to making the molar concentration of your conjugate acid-base pair sufficient to have any capacity at all, you probably want to have it at 0.1 or so, or greater. Henderson-Hasselbalch equation. So I said that you should try to make the molar concentration of your conjugate acid and base, or base and acid, equal. That makes that ratio 1. And the log of 1 is 0. So then in that special case, your pH of your buffered solution will be equal to the pKa of your weak acid. And this is my little sad face. If this ratio goes outside of as greater than 10 or less than 0.1, then it's not going to be good, because you won't have your common ion effect going. So if that's our limit, if this is our limit, 0.1 to 10 as the ratio of the base to the acid, then you're looking at, let's see, how do we say this? The upper limit of the log base 10 of 10 is 1. So you basically are looking at pH is equal to pKa plus 1. Over here, 0.1, the log base 10 of 0.1 is negative 1. So then you're looking at a pH is equal to pKa minus 1. So that's why they say that when you're going to look for a buffered solution with a specific pH, your pH should be plus or minus 1 units of your pKa. And then that's probably where you need to be. All right. So today I want to talk about this is the one of two ways. So you're like, well, how do we get our weak acid and weak base in there? The easiest way is to just take a vat of water and kind of sprinkle both in there. That is totally the best. So physically mix some of the weak acid in its conjugate base. This second one, actually, we're going to hit on Wednesday. It's a little more complicated. Basically, we will start with, and we could go the other way too, but one way is to start with the weak acid, add a strong base, and I'm going to show you on Wednesday how this works. If we add a strong base, it's going to take some of our weak acid and convert it to its conjugate base. And then actually that's how you force the existence, you force into existence this conjugate base. Similarly, we could take a weak base and add strong acid just at the beginning, just to get it going, to create that conjugate acid of the weak base. So let's focus on the first one first. I think I might have two problems. I'm going to erase this.
So when we're dealing with conjugate acid-base pairs, we're not only dealing with those when we're dealing with buffer solutions, or are we?
Right, no. Buffered solutions are use of conjugate acid-base pairs, but conjugate acid-base pairs exist outside of buffered solutions. Yeah, yep. So let's draw a picture. Then we can kind of see where things are kind of entering here. Another beaker. Okay, so what is the pH? So question mark pH. I've read this a few times, so I know it's a buffered solution. So actually, I know I'm going to be using the Henderson-Hasselbalch equation. What is the pH of a buffered solution prepared by dissolving 21.61 grams of sodium benzoate, NaC6H5COO. So you might be like, oh man, what I want you to be thinking behind the scenes is this. Oops, sorry, this is neutral. And I'll just go ahead and draw it up here if that's okay. I want you to be thinking of this thing as falling apart into a sodium cation and C6H5COO minus. And we've been talking about acids and bases, and I'm hoping that when you see something like this, you're like, oh dude, I bet that would accept a proton. So I bet that'd be a cool base. Probably a weak base. And you're right. Problem goes on to say that what I'm going to dissolve it in is not water, but it's actually 500 milliliters of 0.100 molar, drum roll, benzoic acid, C6H5COOH. So I'm going to put WA there. And just like we've been talking about, I've got my weak acid and my weak base floating around in there. So isn't that convenient? So to kind of look at how this is, there's so many different versions of using the Henderson-Hasselbalch equation is the problem. But this one doesn't seem too bad to me because our base, molar concentration of our base, that would be that guy up there. Acetate, we can do that because we got the mass, we have molar mass, we can come up with molar concentration. Molar concentration of weak acid, we've already got it. Log of that ratio, and then pKa, we're going to have to know the Ka for this guy. And then apply the P function. So it's not too bad. So this slide seems like we don't really need it for this problem, but I bet we do for other things. So just bear with me. I told you we need the Ka for our weak acid, and there it is. But if you needed to know the Kb for this guy up here, remember that the relationship between a conjugate acid-base pair is Ka times Kb is equal to Kw. So that's what I've done right here. Kb then is equal to Kw divided by Ka. Kw at 25 degrees Celsius is 1.0 times 10 to the negative 14 divided by Ka, which is 6.3 times 10 to the minus 5th. 2 sig figs, you're looking at a Kb value of 1.6 times 10 to the negative 10. It's getting ready for today, and I'm like, well, we're not using KB in this problem right now. But I think the reason I did this, I think we're doing it for the second problem, is there could be a time when you know KB, but you don't know KA. And then you're going to need KA because you got to use it for your Henderson-Hasselbalch equation. So this is kind of a similar approach, in my defense. So here in a minute, we're going to take negative log of that and plug it into our Henderson-Hasselbalch equation. All right. So we could go either way. Remember, we have two versions of the Henderson-Hasselbalch equation. They just differ by one's the ratio of the molar concentrations of the base to the acid, and one's the ratio of the moles of the base to the moles of the acid. So, yeah, this is one, but on your final exam, you get to bring a sheet, so you can put this on your sheet for your final exam. So looking at this, actually, I can't remember how my notes do it, because we could get to the moles of C6H5COO -1. We could get to the moles of that, we could get to the moles of this, or we could do the molarity, either one. So let's knock out the moles of, looks like I'm going with moles instead of molarity. So to get the moles, we've done this in Chem 1. We're going to use we're getting the moles of the acid, weak acid. So we take the 500 milliliters of solution. We need to get milliliters to liters, so it looks like 1 liter over 1,000 milliliters. And then we can finish up this problem by introducing the molarity, 0.100 moles over 1 liter. And in my notes, I mixed those two terms, but I like it how it came out of my mouth instead of how I have my slides. So that will give us moles. That's not too bad, but I use a calculator. So you're looking at moles of the acid, the weak acid. It's 0.00500 moles of C6H5COOH. So many Chem 1 things. So we need to get the moles of the weak base. And you're going to need to know the molar mass. Do you guys have this molar mass? Okay, the molar mass, 144.10 grams per mole. So we start with 21.61 grams of the compound, the whole salt. So 21.61 grams of C6H5COONA. And we use the flipped version of the molar mass. So if we use 1 mole then of C6H5 and COONA over 144.10 grams of C6H5COONA, grams of the compound cancel. We're left with moles, but now we need to recognize how it ionizes. So we know that we have 1 mole of the weak base, so 1 mole of the C6H5COO -1 over 1 mole of the compound C6H5COONA. And now we have units of moles of the weak base, which is great. 4 sig figs, and we have 0.150 moles of C6H5COO negative. And this almost feels like it kind of reminds me of the ideal gas law equation, where we have stuff and we're ready to plug in. We can't wait to plug in. Okay. So we're ready to, we've done the background information, ready to actually go ahead and use the Henderson-Hasselbalch equation. And there's different ways you might finish this up. Excuse me. What I probably would do is I would take my Ka, which was that 6.3 times 10 negative fifth. I would probably from that knock out my pKa. But here I'm just kind of calculating pKa on the fly here. Plus log of the ratio. And don't forget, it's base over acid. I don't know how you need to memorize that, but when you're looking at a buffered solution, is that somebody's phone?
Here's my phone.
Oh, it might be your parents. So our, excuse me, our base was that C6H5COO -1, and that was 0.150. And the moles of acid we calculated from volume molarity was 0.0500. And then we're ready to clean her up. So you can see I've done it stepwise here, where this first term is the pKa. So you're looking at a pKa of 4.20, and the second term there is the log of the ratio of the moles of base to the moles of acid, 0.48. So we add those two together, and you're looking at the pH of this buffered solution must be 4.68. So that was one where you just poof, made your conjugate acid and your conjugate base both appear in the same solution. So let's do another poof. So we're switching it up. I'll leave my beaker there. I want to do all that work, drawing a nice little beaker. Notice that we are after something a little bit different here. We changed up the conjugate acid-base pairs. So this one says I am going to dump sodium acetate. So CH3COONA, and I'll put a solid there, and I'm going to show it ionizing, breaking apart. So it's going to kick off the sodium +1, and then it's going to leave behind this CH3COO negative, and that's one that actually that is acetate. That's the acetate ion, thus the sodium acetate, and that is going to be a proton acceptor. Weak base. So question mark grams. Do I need to add to then waiting down here? I've got 100 milliliters, 3 sig figs, of 0.125 molar CH3COOH. So what, weak acid? And these are my conjugate acid-base pair. It's a conjugate acid-base pair. Notice what else I have is target pH. When I put target pH, I don't know if I really should. I should put buffered pH. That's better. You want your buffered pH to be equal to 5.00. So if I look at my Henderson-Hasselbalch equation, whichever version I'm going to use, just to kind of think through this, that I already know, 5.00. This actually I'm going to get here in a minute. And it's a little bit of a tease because I know my weak acid. I know this, but I don't know this. That seem right? Okay. So the Henderson-Hasselbalch equation. Again, I might end up using not the molar concentration. I think I'm probably going to use moles, but it's the same thing. So there's a few ways to skin this cat. Right off the bat, though, looks like I don't still. This is a silly problem, but let's just go ahead and do it. The Ka, since acetic acid is a stronger weak acid than acetate, the acetate ion is a weak base, you're not going to find a Kb, but you will find a Ka. So we can knock out the Kb, recognizing that the Kb for a conjugate acid-base pair is equal to Kw divided by Ka. Then Ka was given, and round to 2 sig phase, you're looking at 5.6 times 10 millitons for the Kb for acetate. All right. So back to the problem at hand. We could go ahead and this time I'm going to do a little side calculation. I'm going to knock out what the pKa is using the Ka for acetic acid. So that term is 4.74. And what this says is good choice because you want your target, you want the pH of your buffered solution to be within one pH unit either way. So in this case, you want it between 4, or I don't know which one you want to look at, 4 and 6, and it is. All right, so Henderson-Hasselbalch equation. I'm going to go ahead and rearrange this. Notice that I'm going with the, I don't know if I'm going to stick with going with the molar concentration, but I guess I have it here. Rearranging this, it looks like this, where I'm trying to get to, what I say, my unknown is this guy right up here. That quantity is unknown. I can find everything else, no problem. Now, we've done this before. If we're trying to get to the quantity that the log is of, if I take 10 raised to the log of that quantity, that's equal to that quantity, okay? So that's exactly what I've done for the next one. I simply took 10 raised to this power is equal to this. And then I have to do it on both sides. So I took 10 raised to this power, and that's exactly what you see there. It's the law of logs. So now that's something we're getting closer to being able to isolate the molar concentration of the conjugate base. I kind of call it crisscross, Alsace. So the molar concentration of the conjugate base will be equal to the molar concentration of the acid times 10 raised to the negative, sorry, 10 raised to the difference between the pH and the pKa. So, and then I don't know why I didn't just jump to this version. What's going to be more helpful, instead of going with the molar concentration of base and the molar concentration of acid, is we're going to go with moles. Moles of base and moles of acid. That's going to be better for our particular problem. So, again, then moles of base will be equal to moles of acid times 10 raised to the quantity pH minus pKa. This is just a rearrangement of the Henderson-Hasselbalch equation, this one down here. And the reason I wanted this form is because I'm trying to get to the grams of the base I need to dissolve, okay? So we just need to fill in stuff. So we can get to the moles of acid using the volume and molarity. Looks like this, where 100 milliliters of solution, convert milliliters to liters by 1 liter or 1,000 milliliters. And then introduce the molarity, 0.125 moles of CH3COOH per 1 liter of solution. So 3 sig figs, the moles of the weak acid then are 0.0125 moles. So ding, 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 we're almost done. Because then all we need to do is take 10 raised to the power of pH minus pKa, and we have those values. So plugging in what we know now, the moles of base must be equal to the moles of acid, which we said was 0.0125 moles, times 10 raised to the pH of the buffered solution, 5.00, minus the pKa, which was 4.74. This is one of those where you might want to do it on your calculator a few times to make sure you get the right number. But rounded to 3 sig figs, you're looking at 0.0227 moles of the acetate, CH3COO negative. Now this definitely goes back to a Chem 1 problem. Doesn't mean I can't make a mistake on a Chem 1 problem, but that's the moles we need to get from the CH3COONA. So let's see how we do that. Of course, you'll need the molar mass of the compound, which I didn't show you it, but it's 82.03 grams per mole. notice that if we put the moles required, 0.0227 moles of CH3COO negative times 1 mole of the compound, the salt it's coming from, CH3COONA, per 1 mole of the acetate, CH3COO negative, and this is subscript there. That will give us moles of compound, and then we can use the molar mass of the compound, the unflipped version, which again I should have showed you, sorry about that. But it's 82.03 grams per mole. So 82, final answer, 0.03 grams of CH3COONA per 1 mole of CH3COONA. Goodness gracious. So units will give us grams of the compound, and we're totally done. So 3 sig figs, you're looking at 1.87 grams of the sodium acetate is what you need to dissolve in order to get a buffered solution of 5.00. Voila! So here's where I went ahead and I looked at what was due for part 7. And there's one more part, and we're not going to do that another part because I want to let this settle. The next part we're going to do is a little more tricky. We're going to create its conjugate by adding a strong S or a strong base. So these first, however you want to mark this down, in your assignment for this part, you'll see it goes clear to chapter 14, 101, 102, but reserve those for the next go around. Okay? They're kind of fun in a sad sort of way. So yeah, we have a lab Thursday and then test next Thursday.
And we're doing like a full lab report, right, for this one, and then calculation for the next one.
Mm-hmm. So we don't have calculation for this one?
We do, right?
Yeah.
We do?
Yeah.
Lab report and calculation?
Yeah.
Okay. The whole thing.
Okay. Yeah, this one will be like, yeah, this will be like, wait a minute, no, because it bumps up against a test. So you have to do a full lab write-up for the red cabbage. But, oh, is that what you meant?
Yeah.
Okay, yeah.
Is the whiteboard on Twitter?
I'll put it up there, but I didn't put much on the whiteboard, so I will put it up there. Yeah, there's not much, because I can't do probably fine with the calculations. So red cabbage, full lab write-up.
Yeah.
But then the one that you guys are going to do this Thursday is titration. Remember we did titration?
Yeah.
Not titration. But looking at it a different way. So that one will just be calculations.